yesterday while it rained all day. Put a cover on the engine, and the wind removed that last night, but I think rain was done because nothing seems to be wet. We're going to continue on today. Going to stone up the surface of the pedestal a little bit, cut some 2x4 skids to go on the top surface, and then use the tractor behind the pedestal to winch against, get the engine pulled back into place. Well, that could have gone a lot worse than I expected. I'm actually very pleased at how well it went, and I'm very, very relieved that this is now sitting on a solid foundation. There was a couple times during the move when it was on the beams, I had these nightmare scenarios of, hitting a soft spot under one of the flywheels, having this thing tilt to the point where it either tipped over on its side or the stresses would break the spokes of the flywheel. Thankfully, none of that happened, and everything got pulled off without a hitch. Now, something that isn't very obvious, you may be wondering how this thing was able to do some turns, and have one wheel rotate independently of the other. Both flywheels have two keys. There's a keyway in the crankshaft, and so one of the keys, which has a tapered top surface, is riding in that keyway. The other key, which is also tapered, has a radiused inner surface to match the 3-inch diameter crankshaft. So we pulled the keys off of the far side flywheel, and this flywheel actually now can rotate pretty much all the way around on the shaft and act like a differential. I've heard pros and cons of trying to move an engine like this using the flywheels as support, and some people say, well, the crankshaft can't take that kind of stress. And if this were a steam engine, I would probably say don't attempt it. This is a diesel, and this has a very, very robust crankshaft. The crankshaft is a one-piece forging of high-grade steel, and diesel has really strong pressure pulses, you know, when it fires, and so this crankshaft has to withstand, you know, thousands of pounds of force on the throw, and consequently, you know, the little bit of differential action that it would see with the weight supported on the weight of the engine supported on the flywheel rims, I don't think is nearly as high as what it sees in service when it's running. So I felt safe in doing that. The engine weighs between 2,500 and 3,000 pounds, and I think the flywheels are about 500 pounds apiece. So, you know, 1,000 pounds of that engine weight is just the flywheels themselves. And so the crank is probably only seeing between, you know, 1,500 and 2,000 pounds of weight, with the engine resting, you know, through the flywheel and on the crankshaft itself. So I don't think we stressed it too much in moving it the way we did. We have 4 anchor points. There's 2 in the back and 2 in the front right here, which are good 1-inch diameter holes through the engine frame. We're going to have tie rods going down all the way to the lower block, which is at the bottom of the frame, and there are coupling nuts that go onto 3/4-inch anchors, another 1.5 feet into the center of that underground mass. And so when we get a threaded stud in these anchors, it's going to be going all the way down to the bottom block, so almost 36 inches on the rear one and closer to 48 inches long on the front ones. Now we're going to go with smaller threaded rod than the 1-inch holes, and for a couple of reasons. The older thought on machine anchorage was, you know, you scale these bolts appropriately, and 1-inch seemed about right, but you cannot tighten a 1-inch anchor bolt and get any appreciable amount of stretch. The amount of torque it would take to tighten a 1-inch anchor bolt to where these anchors would actually stretch, you're in the, you know, 1,000 to 2,000 foot-pounds of torque, and we don't want to do that. So we're going to go down to 5/8 on the threaded rods, and we're going to use high-strength threaded rods from McMaster-Carr. They're actually stainless, and they're equivalent to a grade 8 bolt, so you can really torque those up. And even if you torque them to 150 foot-pounds, which is maybe only 60% of their yield, they're going to stretch appreciably being so long. So we're actually going to lengthen those tie rods by torquing them, and that is going to give very good resistance to vibration for the engine moving side to side. Those threaded rods and the nuts on top are never going to come loose. We'll make some shouldered bushings with a thick head. I'll probably make them out of stainless to bush the diameter of the hole down for the 5/8 stud, and that's what we'll cap these off with. We also have to precision level the engine. There's oiling rings in here that will bring oil up to oil the journal surfaces, and if the engine is leaning one way or the other, those rings tend to walk down the downhill side of the crankshaft and they'll rub on the insides of the casting. We don't want that to happen, So we want this crank to be perfectly level, and we'll use the tops of the flywheels, which are machined, to set a precision level across and get this thing perfectly level side to side. Front to back, it's not quite as critical, but we will get the bed casting as level as we can. And we've got it set up to be square to the concrete foundation block within about a 32nd of an inch. That's about as good as we can get, measuring to a somewhat uneven surface. So a little bit about the engine. Ruston Hornsby is an English manufacturer of diesel, actually oil and petrol engines, and semi-diesel engines if you go back far enough. This is actually a fairly late flywheel engine. It's from about 1937, and this particular model is called the Mark CY, and it was designed as a Canadian elevator engine. And not elevator as in people elevator, grain elevator. These engines were made in pretty good quantities to power the apparatus to elevate grain from the bottom of the silo to the top. Now I don't know if that was a belt system or a pneumatic system to convey it, with a blower, but these engines would be running basically all day with very little attention, and it has a self-oiling system, which you can see right here, that is actuated off of a cam on the side crank, and that drips oil to the cylinder, and it drips oil to a special device on the crankshaft to bring oil out to the center eccentric. So this engine's going to run all day with minimal attention as long as it has fuel, and it has free ability for the coolant to circulate. Here's one coolant pipe capped, and there's the other coolant pipe. It was a gravity system, so the coolant would circulate from being heated in the engine. It would rise in the pipes, and you would typically have a tall tank outside the building where the heated coolant would go to the top of the tank, and gravity would bring the slightly more dense cooling water over to the underside of the engine, and there would just be a free circulation of water through the engine. And there's sizing tables in the Ruston Hornsby literature of how many gallons and how tall those tanks need to be to absorb the heat from this engine for a normal day's work. I also got with the engine a radiator, a belt-driven radiator, which obviously was an option, so that you could just run it without the tanks. And we'll be installing that, and probably install that high up in the rafters of the building. And I got what's called a starting bottle, which is an extremely thick-walled pressure vessel shaped like it's kind of like a giant welding cylinder, and that is pressurized to give I think it's 200 psi air to aid in starting the engine. Basically on the front end, this is a starting valve, and you hook your compressed air into the engine here, and when you time the engine, get the piston on the just on the compression side of the stroke, you give it a shot of compressed air, and that'll kick it over, and you time your pressure pulses to get the engine spinning, and then you can throw the fuel lever on and it'll be up and running. So it does have a hand crank. I can't start it with the hand crank. My son was able to, but it's kind of a beast. For such a large engine, it is only rated at 17 horsepower, and it is going to be turning 370 RPM to produce those 17 horsepower. So that's a wrap for this video. If you enjoy what you see, there's a subscribe button in the lower right hand of the channel. Click on that to subscribe. We'll be coming out with more videos showing the rest of the installation. I've got to build an insulated box around this to keep the weather out of it for the next 6 months for the winter. And then once things warm up in the spring, we'll be grouting it, leveling it, grouting it, anchoring it, and we'll do some test runs. I'm anxious to see how rock steady this thing is on this foundation system, and if it's really steady, we should be able to stand a nickel on here with this thing running and not knock it over. So that would be our goal. So that's it. Welcome again to the Engineer's Workshop, and looking forward to having you along on this saga as we build an expansion to this workshop. This, once again, is going to be driving a line shaft and a generator in a metalworking shop edition. Inside this building is all woodworking equipment. We do have a couple of 1900 era line shaft driven lathe and bandsaw, which we can extend a line shaft into that shop, run those pieces of equipment as well. Thanks again, and we'll catch you on the next video.